In question 1, we're asked to express 6x plus 4 over 9x squared minus 4 minus 2 over 3x plus 1 as a single fraction in its simplest form. And I will actually start by factorizing the numerator of the first fraction. So this is giving me 2 brackets 3x plus 2. And the denominator is recognized as the difference of 2 squares. So we're looking at 3x minus 2 times 3x plus 2. And we keep the second fraction as 2 over 3x plus 1. Well, notice that the 3x plus 2 will cancel out, and I will be expressing everything over the same denominator of 3x minus 2 times 3x plus 1. So the first term will be multiplied by 3x plus 1 to give me 2 brackets 3x plus 1 minus 2 brackets 3x minus 2. I will expand the numerator to get 6x plus 2 minus 6x plus 4, and all of it over the 3x minus 2 times the 3x plus 1. And we notice that the 6x with the negative 6x will cancel out, and therefore this leads to 6 over the denominator of 3x minus 2 times 3x plus 1. In question 2a, we need to show that the equation f of x is 0, where f of x is defined to be the cubic here, can be written in this form. So obviously I'll have to start with x cubed plus 3x squared plus 4x minus 12 is equal to 0. And I need to come up with a rearrangement that will take me to the printed answer here. Well, the first thing to do is keep the x cubed plus the 3x squared on the left hand side and move the 4x minus 12 on the right hand side. So this is equal to 12 minus 4x. Well, we can see that there's a common factor of x squared on the left hand side, so x squared times x plus 3. And on the right hand side, we've got a common factor of 4, so 4 brackets 3 minus x, which leads to x squared is equal to 4 times 3 minus x over the x plus 3. And therefore, all I need to do is take the square root of the right hand side, so we're looking at the square root of 4 times 3 minus x over x plus 3 as required. In part B, we're asked to use the given iteration formula together with the starting value of x naught being 1 to find to 2dp's the values of x1, x2, and x3. So we know that we are starting at x naught being equal to 1. So I'm going to go on my calculator. I press 1 and equals. So that means I've stored the 1 on my answer key. Then we've got the square root of 4 brackets 3 minus the uns over the 3 plus the uns. So every time I press the equal sign, it's a new iteration. So I press it once and I get root 2, which is 1.414. Remember, we need to give answers correct to 2dp. So x1 is 1.41. I press the equal sign again. I get x2 to be 1.20, correct to 2 decimal places. And I press the equal sign once more and I get x3 to be 1.31. In part C, we are told that the root of f of x is 0 is alpha, and we need to choose a suitable interval to prove that alpha is 1.272, correct to 3 decimal places. Well, if we consider the 1.272, we need to choose a tied interval around this value and look for a change of sign. So I'm going to go for 1.2725 and 1.2715, and I will be evaluating f of 1.2725 and f of 1.2715, hoping for a change of sign. Remember, we always look for a change of sign in what we need to be equal to 0, and in this case it's f of x. So I'm going to go on my calculator. I press 1.2725 and I press the equal sign to store it on my answer key, and then I will be evaluating f of 1.2725. So this is uns to the power of 3, and then we've got plus 3 uns squared, and then we have the plus 4 uns minus 12. If I press the equal sign, I get an answer of 0.00827. And then I want to do f of 1.2715. So I'm just going to press 1.2715 and the equal sign. And then I go 1 up, the cursor key pointing upwards. I get the same expression now with the new value for the answer key. If I press the equal sign, I get negative 0.008 to 1. So we've got one being greater than 0 and the other being less than 0, which means we can conclude that there's a change of sign and f of x is continuous. Therefore, alpha lies between 1.2715 and 1.2725, and any value within this interval has to give me a rounded answer of 1.272 correct to 3 dps as required. Remember that you need to mention the change of sign as well as the continuity of f of x in order to get all marks in this part of the question. So in question 3, we've got the figure showing a sketch of f of x is 2 modulus of 3 minus x plus 5 for x being greater than or equal to 0, and we need to solve the equation f of x is a half x plus 30. Well, the first thing to do is identify each line segment with their individual equation. So on the right hand side, we are looking at y is equal to negative 2 brackets 3 minus x plus 5. Well, I chose the negative here because I see that the straight line is going uphill, so I must be having a positive gradient. So I need a negative sign here to make it positive with the negative sign within the bracket. Well, if I expand this, I get y to be negative 6 plus 2x plus 5, leading to y is 2x minus 1. Whereas on the left hand side, we are looking at y is equal to 2 brackets 3 minus x plus 5. I will expand this to get 6 minus 2x plus 5, and therefore we're looking at y is minus 2x plus 11. From this equation, we can see that the cut on the y-axis must be at 11, and if we consider the right-hand side of the equation that we need to solve, the half x plus 30, we're looking at a straight line going uphill, certainly less steep than this line here, which has a gradient of 2, and cutting the y-axis here at 30. So to find the solution, there is only one solution, a point of intersection on the right hand side here. We simply need to equate the 2x minus 1 with the half x plus 30. I will multiply everything by 2 to get 4x minus 2 is equal to x plus 60, which leads to 3x is equal to 62, and therefore x is equal to 62 over 3. In part B, we've got that the equation f of x is k, where k is a constant, has two distinct roots, and we need to state the set of possible values for k. So I will briefly go back to the diagram here. The line y equals to k is simply a horizontal line. So if I move it a bit up or down, we can see that we've got one solution, and then from this point onwards, we've got two solutions, and then it's one solution if I go through the vertex, and then no solutions. So obviously we need to be below or equal to 11 and certainly greater than the vertex here. So we start by finding the vertex. Well, to find the vertex, the only thing I need to do is consider when the modulus part will be 0, and this will be 0 when x is 3, and if x is 3, then y is 5. So we have that the vertex here is at 3, 5. We know that k must surely be greater than 5 and less than or equal to the 11, the y-intercept on the left-hand side, and therefore we can safely conclude that we've got 5 less than k less than or equal to 11. In 4i, we need to find the integral of 1 over 2x minus 1 from 5 up to 3, writing our answer in its simplest form. So starting with the given integral, we know that the 1 over 2x plus 1 will give me ln of 2x minus 1, but I also need to divide by the derivative of the bracket, so we've got a half there, and we've got the limits of 5 and 13. Now I will substitute the upper limit to give me a half ln of 2 times 13 minus 1, and then we've got minus a half ln of 2 times 5 minus 1. This gives me a half ln of 25 minus a half ln 9. I can combine the two together because when we've got ln minus ln, I can write as the ln of the quotient. So this is giving me a half ln of 25 over 9, but I'm not done. There's a simpler form I need to arrive at. I can take the half up as a power, so we're looking at ln of 25 over 9 raised to the power of a half, which gives me ln of 5 over 3, which is the final simplified answer. In II, we need to use integration to find the exact value of the integral of sine 2x plus sec over third x tan over third x dx from 0 up to pi over 2. Obviously, we are in radians because any integral is always in radians. It's never in degrees. So we know that the integral of sine is negative cos, and I also need to divide by the derivative of 2x. So this is giving me minus a half cos of 2x, and then the integral of sec tan is simply sec, but I also need to divide by the derivative of a third x, which is a third. So we've got plus 1 over 1 over 3 times sec over third x, and we've got the limits of 0 and pi over 2. Well, this simplifies to minus a half cos of 2x plus 3 sec of x over 3 from 0 up to pi over 2. I will start by substituting the upper limit of pi over 2, so I've got minus a half cos of 2 times pi over 2 plus 3 sec of pi over 2 divided by 3. So that's the upper limit substituted, minus a half cos of 0 plus 3 sec of 0. I have substituted the lower limit of 0. So this is giving an answer of a half plus 3 times 2 root 3 over 3. This is the sec of pi over 2 divided by 3 minus the minus a half plus 3, which simplifies to give me 2 root 3 minus 2. In question 5, we've got y to be 5x squared minus 10x plus 9 over x minus 1 squared. And we need to show that the y dx is k over x minus 1 cubed, where k is a constant to be found. Obviously, I need to apply here the quotient rule of differentiation. So I differentiate the top to get 10x minus 10, and I keep the bottom of x minus 1 squared, minus I keep the top of 5x squared minus 10x plus 9, and I differentiate the bottom of x minus 1 squared, which means I get the power down, I deduct 1 from the power times the derivative of the bracket, and all of it expressed over the denominator raised to the power of 2. So x minus 1 squared raised to the power of 2 will give me x minus 1 raised to the power of 4. Well, we can see that x minus 1 is a common factor in the numerator, and we are left with 10x minus 10 times x minus 1 minus 2 times 5x squared minus 10x plus 9 over the denominator of x minus 1 raised to the power of 4. I immediately see that I can simplify the x minus 1 with the x minus 1 to the power of 4 to leave me a power of 3 in the denominator, and I will expand and simplify the numerator to get 10x squared minus 10x minus 10x plus 10 minus 10x squared plus 20x minus 18, and all of it divided by x minus 1 raised to the power of 3. We can immediately see that the 10x squared with the negative 10x squared will cancel out, and the minus 10x will go away with the 20x. Well, 10 minus 18 is simply negative 8, and we've got negative 8 over x minus 1 raised to the power of 3 as the expression for the y dx, which means I can conclude that k is equal to negative 8. In question 6, we've got f of x defined to be e to the x plus 2 for all x belonging to the real numbers, and we need to state the range of f. Well, we know that e to the x is always greater than 0 for all real values of x. That's my starting point. So if I add 2, I get e to the x plus 2 is certainly greater than 2, which means that f of x is greater than 2. Remember that the range is the output, it's the y values that you can get out of f of x. So what we have done here, we have started from e to the x being greater than 0, and we have reconstructed the expression for f of x, arriving at f of x being greater than 2. In part B, we need to find f of g of x, giving our answer in its simplest form. So we're looking at a composite function. We know that we always start from the inside, and we have that g of x is ln x. So we've got f of ln x, which means we're looking at e to the ln x plus 2 which is equal to x plus 2. This is the composite function f of g of x, which needs to be accompanied with its domain. Well, the domain is all values of x belonging to the real numbers, but we need x to be greater than 0 because we started with g of x, and g of x had a domain of x being greater than 0, which means the starting point, the domain of f of g of x, has to be all x being greater than 0. In part C, we need to find the exact value of x for which f of 2x plus 3 is equal to 6. So f of 2x plus 3 is simply e to the 2x plus 3 plus 2 is equal to 6. So we're looking at e to the 2x plus 3 is equal to 4. I will take ln of both sides to get 2x plus 3 is equal to ln 4, and therefore 2x is equal to negative 3 plus ln 4. If I divide throughout by 2, I get x to be minus 3 plus ln 4 divided by 2, which is my final exact answer for x. In part D, we need to find f inverse stating its domain. So we will start by expressing f of x in the form of y is equal to the e to the x plus 2. I will now interchange x and y. So we've got x is equal to e to the y plus 2, which means that x minus 2 is equal to e to the y, and therefore ln of x minus 2 is equal to y. So we can conclude that f inverse of x is equal to ln of x minus 2, but we also need to provide the domain of f inverse. Well, the domain of the inverse is the range of the original of f of x, and we have found previously the range to be all y's being greater than 2. So in this case, for f inverse of x, the domain will be x belonging to the reals and x being greater than 2. In part D, we need to sketch the graph of f of x and f inverse of x, given the coordinates of all the points where the curves cross the axis. So I will start by drawing my x and y axis. Remember that f of x is e to the x plus 2. We have already established that the range of f of x will be all values of y greater than 2, because simply the line y equals to 2 is a horizontal asymptote. So the graph of e to the x plus 2 looks something like this. Now the graphical relationship between f of x and f inverse of x is that one is a reflection of the other along the line y equals to x. So if I draw the line y equals to x, the first thing I observe is that the horizontal asymptote will become a vertical asymptote. So this will be the line with the equation x is equal to 2. And if I reflect f of x, I see something like this. That's f inverse of x. You can see the symmetry about the mirror line of y is equal to x. And the only thing missing is for us to determine the cuts on the axis. Well, to find the cut on the y-axis for f of x, I will simply evaluate f of 0. So I'm putting x is 0. This gives an answer of 3. And therefore, we can see that the cut on the y-axis is 3, and this is mirrored on the x-axis for f inverse of x. So the cut on the x-axis for f inverse of x is simply 3, which completes the answer to part E. In 7a, we've got the point P lying on the curve with equation x is 4y minus sine 2y and all squared, where the coordinates of P are P comma pi over 2, and we need to determine the exact value of P. So I will simply start by substituting y is pi over 2 into the expression for x. So this leads to x being equal to 4 times pi over 2 minus sine times 2 times pi over 2, and all raised to the power of 2. Well, if you plug this on the calculator, you get an answer of 4 pi squared. In part B, we've got that the tangent to the curve at P cuts the y-axis at the point A, and we need to use calculus, which means differentiation, to find the coordinates of A. So I will start by determining an expression for dx dy. So in this case, we are applying the chain rule. So we get the power of 2 down, so it's 2. We deduct 1 from the power, so 4y minus sine 2y. And we also multiply by the derivative of the bracket, which is the 4y minus sine 2y. Well, the derivative of this is simply 4 minus 2 cos of 2y. So this is the expression for dx dy. Well, I will evaluate this at y is pi over 2. So dx dy when y is pi over 2 will be found by substituting y with the value of pi over 2. So we're looking at 2 times 4 pi over 2 minus sine of 2 times pi over 2, and the second bracket is 4 minus 2 cos of 2 times pi over 2. Well, this gives an answer of 24 pi, and to find the gradient of the tangent, all we need to do is take the reciprocal of dx dy, because the gradient of the tangent is given by dy dx. So this is going to be 1 over 24 pi. And since we've got the point, its coordinates, and the gradient of the tangent, I will simply be using y minus y1 is mx minus x1 to proceed in finding the equation of the tangent. So we're looking at y minus pi over 2 is equal to 1 over 24 pi times x minus the 4 pi square we obtained in part A. So we are looking at the cut on the y-axis. So at point A, this means that x is 0, which leads to y minus pi over 2 is equal to 1 over 24 pi times 0 minus 4 pi squared. This leads to y minus pi over 2 is equal to negative pi over 6, which means that y is equal to pi over 3, and therefore the coordinates of A are 0, pi over 3. In question 8, we've got an experiment where the number of microbes capital N in the culture capital T days after the start of the experiment was counted, and we've got that the relationship is of the form N is AT to the B, and we need to show in part A that this relationship can be expressed in the given form. So starting with what we are given, N is AT to the B, it makes sense to start by taking the log base 10 of both sides. So we're looking at log of n base 10 is equal to log base 10 of a t to the b. I will then use the product rule of logarithms to split the right hand side into log of a base 10 plus log of t to the b base 10, which can be written as log of n base 10 is equal to log of a base 10 plus b log t base 10, using the power law of logarithms. Now if we compare with what we were given, which is log n is m log t plus c, then we can see that the log of a base 10 is the constant, is the c, and then the b is the m. So we can safely conclude that m is equal to b and c is equal to log of a base 10. In part B, we've got the line of best fit shown on the graph here, where log n is plotted against the log t, and we need to use the information provided to estimate the number of microbes present in the culture 3 days after the start of the experiment. Well, obviously we're dealing with a straight line. I need to determine 2 points that lie on the line. So I can see we've got the point 0.1, 2.05, as well as the point 1.2, 4.55, and I'll be using these 2 points to determine the equation of the straight line. I will start with the gradient, so we're doing rise over run here. So m is 4.55 minus 2.05 over the run, which is 1.2 minus 0.1. This gives an answer of 25 over 11, which means we can use y minus y1 is mx minus x1 to proceed with the equation of the straight line. Well, dy is simply the log of n base 10 minus, I will pick one of the 2 points. I'll pick the 0.1, 2.05. So minus 2.05 is equal to 25 over 11, and the x is the log of t base 10 minus the 0.1. Well, we know that we need to estimate the number of microbes 3 days after the start of the experiment, which means that capital T is equal to 3, and therefore we've got log of n base 10 minus 2.05 is 25 over 11, and we've got in brackets log of 3 base 10 minus the 0.1. So this leads to log of n base 10 is equal to 2.90709 ... If I plug the right hand side on the calculator and add the 2.05 as well, this gives n to be 10 to the power of 2.90709 ... If you plug this on the calculator, you get that n is 807 microbes. the examiner here is accepting anything which rounds to 800 because you might have picked different points on the line and you might get a somewhat a different answer to the 2.90709 I got here. Anything rounding to 800 will be acceptable by the examiner. In C, we are asked with reference to the model to interpret the value of the constant a. Well, the model was capital N is at to the b, and we can see that when t is equal to 1, then n is simply a times 1 to the power of b, which is a, and therefore we can easily conclude that a is the number of microbes present in the culture 1 day after the start of the experiment. In 9a, we are asked to prove that sec of 2a plus tan of 2a is equivalent to cos of a plus sine a over cos a minus sine a. Well, it's the classic first part of a trigonometric question where you need to show an identity is true. So you can either go from left to right or from right to left, but in any case you need to be showing every single step along the way to claim full marks. Well, in this case I will start from the left hand side. We are looking at sec of 2a plus tan of 2a. Well, we know that sec is 1 over cos, so we've got 1 over cos of 2a, and tan of 2a is sine of 2a over cos of 2a. Well, we can see that cos of 2a is a common denominator, so we've got 1 plus sine of 2a over the cos of 2a. Well, I will write the 1 in the numerator as cos squared a plus sine squared a, and then the sine of 2a is simply 2 sine a cos a. Whereas in the denominator, the cos of 2a, I will use the double angle for cos to write this as cos squared a minus sine squared a. And this is done because the numerator is now a perfect square. We're looking at cos of a plus sine of a all raised to the power of 2, or simply cos a plus sine a times cos a plus sine a. Whereas in the denominator, we're looking at the difference of two squares. So we've got cos of a plus sine a times cos of a minus sine of a. And of course, we can see we've got some simplifications. We've got the cos a plus sine a cancelling out, and we're left with cos of a plus sine of a in the numerator, and in the denominator, we've got cos of a minus sine of a, which is exactly the left-hand side as required. In part B, we are asked to solve for theta between 0 and 2 pi. Sec of 2 theta plus tan 2 theta is a half, giving our answers to 3 dp's. And the word hence here means that we have to use the result from part A, otherwise we will score 0. Well, we can see that sec of 2 theta plus tan 2 theta is simply cos theta plus sine theta over cos theta minus sine theta, and this is equal to a half, which means we can proceed by cross multiplying to get 2 brackets cos theta plus sine theta is equal to cos theta minus sine theta. I will expand the left hand side to get 2 cos theta plus 2 sine theta is equal to cos theta minus sine theta. This leads to 3 sine theta is equal to negative cos theta. And I will proceed by dividing both sides by cos theta. So we're looking at 3 sine theta over cos theta is equal to minus cos theta over cos theta, which is of course 3 tan theta is equal to negative 1, and therefore tan of theta is negative a third. I will proceed in finding the PV. So the PV is simply shift tan of minus a third, and this gives an answer of minus 0.32175 ... and I'll be using the generating formula for tan. So theta is the PV of minus 0.32175 ... plus pi k. Remember, we're between 0 and 2 pi, and we need to be giving our answers to 3 decimal places. So if we put k to be 1, we get 2.820, and if we put k to be 2, we get 5.961. In question 10, the amount of antibiotic in the bloodstream is given by X is capital D e to the negative 0.2 t, where capital D is the initial dose in milligrams and t is the time in hours after this dose has been administered. We initially have 15 milligrams of the antibiotic given, and we need to use the model to find the amount of antibiotic 4 hours later. So essentially we're looking at the value of X when capital D is 15 and T is 4. So this is X equal to 15 e to the negative 0.2 times 4. If we plug this on the calculator, we get an answer of 6.740 milligrams. We are then told that the second dose of 15 milligrams is given 5 hours after the first dose has been given, and we need to show that the total amount of antibiotic 2 hours after the second dose is given works out to be 13.754 milligrams to 3 decimal places. Well, we need to realize here that the total amount 2 hours after the second dose is simply the amount due to the first dose and the amount due to the second dose. So 2 hours after the second dose has been given, we've got the initial dose being in the bloodstream for 7 hours. So the amount here is going to be 15e to the negative 0.2 times 7. And then we've got the amount due to the second dose, which has been in the bloodstream for 2 hours. So this is 15e to the negative 0.2 times 2. If we plug this on the calculator, we get 13.753755 ... which works out to be 13.754 milligrams as required. We are then told that no more doses of the antibiotic are given, and at time capital T hours after the second dose being given, the total amount in the bloodstream is 7.5 milligrams, and we need to show that T is A plus ln B plus B over E, where A and B are integers to be determined. Well, we will follow a similar approach to part B. So we've got a total amount of antibiotic of 7.5 milligrams, and this is partly due to the first dose, which has been in the bloodstream for capital T plus 5 hours, so 15 e to the negative 0.2 brackets T plus 5, and the rest of it is due to the second dose, which has been in the bloodstream for capital T hours, so 15 e to the negative 0.2 T, and we need to solve for T. So the first thing to do is divide throughout by 7.5. So we get 1 is equal to 2e to the negative 0.2 t minus 1 plus 2e to the negative 0.2 capital T. What I will do next is divide throughout by e to the negative 0.2 t. This will lead to some nice simplifications over the right hand side, and will also yield an e to the 0.2 capital T term on the left hand side. So we're looking at e to 0.2 t is equal to 2e to the negative 1 plus 2. So I can write now that e to the 0.2 capital T is 2 over e plus 2. This is nice because we are starting to get the expression within the ln here. The next logical thing is to take a ln of both sides. So we're looking at 0.2 capital T is equal to a ln of 2 over e plus 2. And if I multiply both sides by 5, we get the left hand side to be t and the right hand side to be 5 ln of 2 over e plus 2, and therefore we can conclude that the constant a is 5 and the constant b is 2.